Hey everyone, Mr. Hauk here. In today's lesson, we're going to be looking at what we call reciprocal trigonometric ratios. We're going to be looking at standard position, coterminal angles, and reference angles, and we're going to be exploring even and odd symmetry as it relates to trigonometric functions. Let's go ahead and get started. So, notice here in this image we have a right triangle. Our angle theta is right here in the bottom left corner. And I've gone ahead and labeled the sides. So relative to the angle theta, we have our adjacent side, our opposite side, and our hypotenuse. So we've already discussed the sine, cosine, and tangent of theta. We know that the sine is the opposite leg divided by the hypotenuse. We know the cosine of the angle is the adjacent leg divided by the hypotenuse. And we know that the tangent of theta is the opposite leg divided by the adjacent leg. There are actually three other trigonometric functions. There's the cosecant of theta, which is the hypotenuse divided by the opposite. There's the secant of theta, which is the hypotenuse divided by the adjacent. And there's the cotangent of theta, which is the adjacent leg divided by the opposite leg. Notice that the cosecant of theta is the reciprocal of the sine of theta. The secant of theta is the reciprocal of the cosine of theta. And the cotangent of theta is the reciprocal of the tangent of theta. So that's why we call these the reciprocal trigonometric functions. So in symbols, this is what we have to represent our six trigonometric functions. We have that the sine of theta is equal to 1 over the cosecant of theta. The cosine of theta is equal to 1 over the secant of theta. The tangent of theta is equal to 1 over the cotangent of theta. The cosecant of theta is equal to 1 over the sine of theta. Secant of theta equals 1 over cosine of theta. And that the cotangent of theta equals 1 over the tangent of theta. So they are reciprocals of each other. We also know that the tangent of theta is equal to sine of theta divided by the cosine of theta. We've already established that. So this implies that the cotangent of theta, since the cotangent is the reciprocal of the tangent of theta, this implies that the cotangent of theta is equal to the cosine of theta divided by the sine of theta. Okay? So let's try some problems here real quick, just to get a feel for this. So here we have that the sine of theta is equal to 5 over 13, and we want to find the cosecant of theta, assuming that the angle theta is between 0 and 90 degrees. So the angle theta is an acute angle. So here's what we know. We know that, well, since the cosecant of theta is equal to 1 over the sine of theta, well, that means that the cosecant of theta is equal to 1 over 5/13, since we know that the sine of theta is equal to 5 over 13. Well, 1 over 5 over 13, that's 1 over 1 times 13 over 5, which is 13 over 5. So the cosecant of theta is 13 over 5. In our next example, given the right triangle to the right, we want to find all 6 trigonometric ratios. So we'll start with the sine of theta. Let's get off the auto shape recognizer. So we'll start with the sine of theta. We know that the sine is the opposite leg divided by the hypotenuse, so opposite of theta would be square root of 21. Hypotenuse would be 5 since it's across from the 90-degree angle. So the sine of theta is square root of 21 over 5. The cosine of theta, which is the adjacent leg, adjacent to theta is 2. The adjacent leg 2 over the hypotenuse 5. And then we have the tangent of theta, which is the opposite leg, square root of 21, divided by the adjacent leg, which is 2. Now looking at the cosecant of theta, well, we know that the cosecant is 1 over the sine of theta. So if I did 1 over square root of 21 over 5, we would get 5 over the square root of 21. Now I'm going to do a little bit of math down here real quick though. So 5 over the square root of 21, we don't like square roots in the denominator. So let's multiply both the numerator and denominator by the square root of 21. So this is going to give us 5 square root of 21 in the numerator, and in the denominator, square root of 21 times itself, square root of 21, is just 21. So the cosecant of theta, simplified, will be 5 square root of 21 over 21. Okay? The secant of theta, Well, that's 1 over the cosine of theta, so 1 over 2/5 would be 5/2. And then the cotangent of theta is 1 over the tangent of theta, so instead of square root of 21 over 2, we would get 2 over square root of 21. But once again, we don't like square roots in the denominator, so let's multiply both the numerator and denominator by the square root of 21. And this is going to give us 2 square root of 21 over 21. All right. So those are our 6 trigonometric ratios specific to that right triangle. So now let's talk about something called the standard position, coterminal angles, and reference angles. So an angle that's in standard position if the vertex of the angle is at the origin. So we can see right here, vertex is at the origin, with one ray on the positive side of the x-axis. This ray is called the initial side. So right here, this ray is called the initial side. And the other ray is called the terminal side. So here's our initial side. We call this the terminal side. And we can see that our vertex is there at the origin. So we call that standard position. The measure of the angle is determined by rotating from the initial side to the terminal side. So we start at the initial side, we rotate to the terminal side, and that's the measure of our angle. So right here. The measure of the angle is positive when we move in a counterclockwise direction. So counterclockwise would be that direction. And the measure of the angle is negative if we move in a clockwise direction, which would be that direction. So in this particular example, if I moved in the counterclockwise direction, this would be about, we'll say this is 135 degrees, and that's a positive angle measure. If I were to rotate in the other direction, so if I were to rotate clockwise instead of counterclockwise, so starting from the initial side and rotating clockwise, well, since we're rotating clockwise, we would have a negative angle measure, and it would be about negative 225 degrees. Okay. We call two angles that share the same initial side and terminal side, we call them coterminal angles. And it's actually pretty easy to find coterminal angles. When we're talking about degrees, all we have to do is take your angle measure and either add or subtract multiples of 360. So that's what this right here represents. This looks like a somewhat complicated expression, theta plus or minus n times 360 degrees, where n is an integer greater than or equal to 1. All that's saying is to take your original angle, theta, and add or subtract multiples of 360 degrees. So to give you an example, let's say that we had 45 degrees. Well, every time that I would add 360 degrees, let's actually do this a little bit differently. So let's say we have 45 degrees. So if I added 360 degrees to that, so 45 degrees plus 360 degrees, that would give us 405 degrees. That 405 degrees is a coterminal angle to 45 degrees. And if I took that 405 degrees and added another 360 degrees to it, so plus 360, I would get 765 degrees. And that 765 degrees would also be coterminal to 45 degrees. So every time we add 360 degrees or a multiple of 360 degrees, we would have a coterminal angle. And the same works in the negative direction. If I took 45 degrees and subtracted 360 degrees or a multiple of 360 degrees, those would be coterminal angles as well. The same thing works for radian measures instead of degree measures. So if I took an angle in radians and I added or subtracted a multiple of 2 pi, since we know 2 pi and 360 degrees are equal to each other, if I added a multiple of 2 pi or subtracted a multiple of 2 pi, then I would also have a coterminal angle. So let's try that out here. And actually, let's look at a couple examples. So 135 degrees is a coterminal angle to negative 225 degrees, because if I took 135 and subtracted 360 degrees, I would get negative 225. Same deal with this 3 pi over 4 radians. If I took 3 pi over 4 radians and subtracted 2 pi, I would get negative 5 pi over 4 radians. So let's look at a couple examples. Can we think of a positive and negative coterminal angle for 260 degrees? Well, to get a positive coterminal angle, well, let's just take the 260 degrees and let's add 360 degrees to it. So 260 degrees plus 360 degrees, that would give us 620 degrees. So 620 degrees would be a positive coterminal angle for 260 degrees. If I wanted to find a negative coterminal angle, well, I could subtract 360 degrees, and that would give me negative 100 degrees. So negative 100 degrees would be a negative coterminal angle for 260 degrees. But keep in mind, for these two, these are not the only positive or negative coterminal angles. I could continue to add multiples of 360, or I could continue to subtract multiples of 360 and continue to come up with more coterminal angles for 260 degrees. Okay? Let's try the next one. Can you think of a positive and negative coterminal angle for 5 pi over 18? Well, to get a positive coterminal angle, I could take 5 pi over 18. We could add 2 pi to it, since 2 pi is the same as 360 degrees. And if I added 5 pi over 18 plus 2 pi, this would give me 41 pi over 18. Now some of y'all might be saying, wait, Mr. Houck, slow down. How does 5 pi over 18 plus 2 pi equal to 41 pi over 18? Well, let's do a little bit of side math up here. 5 pi over 18 plus 2 pi. Well, I would need to rewrite 2 pi so that it has the same denominator as 18. So 5 pi over 18 plus 36 pi over 18. So notice I'm rewriting the 2 pi as 36 pi over 18. And then when you add 5 pi plus 36 pi, this gives us 41 pi over 18. So I got common denominators, added the numerators together, kept the denominator the same, got 41 pi over 18. Okay? Now let's find a negative coterminal angle for 5 pi over 18. So let's do 5 pi over 18, and this time let's subtract 2 pi. Well, if I take 5 pi over 18 minus 2 pi, I would end up getting negative 31 pi over 18. All right. Next, we call the acute angle formed between the terminal side and the x-axis the reference angle. Note that the reference angle is always going to be positive. So if we take, for example, here this 135 degrees, well, here's our terminal side. And if I look at the terminal side and the x-axis, this is the reference angle here in blue. And that reference angle in this case would be 45 degrees. So again, the reference angle is the angle that is between the terminal side and the x-axis, and it is always going to be positive. Okay? So a question that might come up is, well, why might reference angles be useful? Well, it turns out that angles with the same reference angle will always have the same trig values. So let's go ahead and write that down. Angles with the same reference angles with the same reference angles always have the same trig values. However, it's important to note that the sign may vary. So signs may vary. Signs as in positive or negative. Signs may vary. So here's an example. If we look at the sine of 45 degrees, okay, sine of 45 degrees. Well, the sine of 45 degrees is approximately 0.707, but that's square root of 2 over 2. okay, as an exact answer. Well, the sine of 135 degrees is also square root of 2 over 2. And 45 degrees and 135 degrees, they have the same reference angles. They both have a reference angle of 45 degrees. So their sine values are the same. But again, keep in mind that little caveat that the signs may vary, meaning that one may give you a positive, one may give you a negative, okay? But the value itself will be the same. All right, the last thing we want to look at is exploring symmetry of our trig functions. And first we're going to look at symmetry algebraically, and then we're going to explore trig function symmetry graphically. So just to save us a little bit of time, here in the notes it says use the unit circle to answer the following. So we were asked to find the sine, cosine, tangent, cosecant, secant, and cotangent of several different angles. Notice that we are finding positive angles and then negative angles. So for example, we're taking the sine of 30 degrees and the sine of negative 30 degrees. And we're getting that the sine of 30 degrees is 1/2 and that the sine of negative 30 degrees is negative 1/2. We found that the tangent of 60 degrees is square root of 3, and the tangent of negative 60 degrees is negative square root of 3. We can see that for the cosine of 90 degrees is 0, same thing for the cosine of negative 90. The cosecant of pi over 3 is 2 root 3 over 3. The cosecant of negative pi over 3 is negative 2 root 3 over 3. Also, looking at the cotangent of 45 degrees is 1. The cotangent of negative 45 degrees is negative 1. And so on and so forth. The purpose of looking at all these different values is to talk about even and odd functions as they relate to the trigonometric functions. So recall from algebra that an even function is a function such that f of negative x equals f of positive x. So what that means is if I take a function and I plug in a negative input, I'm going to get the same output as if I plugged in the positive version of that input. So, for example, let's look at the cosine. Let's look at this example right here. If I plug in pi, so if I take the cosine of positive pi, I got negative 1. But even if I plugged in the cosine of negative pi, notice that I get negative 1 again. So that would be an even function. Let's see if we can find any more even functions. Well, I see something right here. If I look at the secant, well, if I did the secant of pi over 6, I would get 2 root 3 over 3. But if I calculate the secant of negative pi over 6, I still get 2 root 3 over 3. So it's looking like the cosine and the secant are even functions. So let's go ahead and record that down. The cosine and the secant, so this is cosine and secant, are even functions. So odd functions are functions such that f of negative x equals negative f of x. So to give you an example of that, let's look at the sine. So our first example here was the sine of 30 degrees and the sine of negative 30 degrees. Well, the sine of 30 degrees gave us positive 1/2, but the sine of negative 30 degrees gave us a negative 1/2. We can see the same thing in the tangent. If I took the tangent of 60 degrees, I would get square root of 3. If I took the tangent of negative 60 degrees, I get negative square root of 3. So far we have the sine, we have the tangent, see if we can find any others. Well, if I look at the cotangent of 45 degrees is positive 1, but the cotangent of negative 45 degrees is negative 1. So we also have the cotangent. And let's look at the cosecant, because we haven't taken a look at cosecant yet. Well, if I look at the cosecant of pi over 3 is 2 root 3 over 3. Cosecant of negative pi over 3 is negative 2 root 3 over 3. So the cosecant would also be odd. Now, this is not pure coincidence. If we think about the cosine and the secant, well, we talked about earlier that the cosine and the secant are inverses of each other. So it would make a lot of sense that they're both even functions. Same with the sine and the cosecant. Sine and cosecant are inverses, and tangent and cotangent are inverses. So since the sine is odd, the cosecant's going to be odd. Since the tangent is odd, it makes sense that the cotangent is odd as well. Now let's look at this in a more graphical lens. So notice that we have this image here, so we have our unit circle, and we have our point here, and we know that, here in the first quadrant, this point would be cosine theta, comma, sine theta. Well, if I were to take this point and reflect it across the x-axis, then cosine theta, sine theta would become cosine theta, negative sine theta. Okay, so for essentially for this right here, we can see that when we reflect it across the x-axis, the cosine kept its sign, but the sine ended up changing sign. So that's more of a graphical view as to why cosine is a even function, but sine is an odd function.